All right, let's get started. Hi, everyone. My name is Dimitra Tri. I'm at the Center for Space Science at NYU Abu Dhabi. And welcome everybody to the Space Science webinar series hosted by the Center for Space Science and the UAE Space Agency. Before we get started with today's talk, I have an announcement to make. As you all know that UAE's Mars mission, the Emirates Mars mission HOPE is going to be launched on July 15th. Then later in the month, we have a mission from China. And after that, on July 30th, NASA's Mars 2020 mission is going to be launched. And to celebrate the occasion, we are going to host a virtual symposium on July 14th. So it is going to be next Tuesday, same time. You don't have to register. If you are listening to this, if you're registered for our seminar series, you don't have to register again. We have speakers from Mars 2020, from the Emirates Mars mission, from ISRO's Mars Orbiter mission, MAVEN, etc. So it is going to be an exciting event. And we hope you can join us. Please spread the words to your colleagues, friends who might be interested in this. So let's get started. Our today's speaker is Dr. François Leblanc. He got his PhD from University of Paris in '98. He did a postdoc at University of Virginia in the US. Then moved back to Europe, did a couple of postdocs, then joined the CNRS, the French National Center for Scientific Research. He is now the Deputy Director of LATMOS. It is the major research center on planetary atmospheres in France. He's involved with a number of space missions. He is the PI on several important projects. He's a world-leading expert on the Martian atmosphere. He's also closely involved with NASA's MAVEN mission, which has taught us so much about the Martian atmosphere. So we are really excited to have him. So François, welcome to NYU Abu Dhabi, and please get started.
We hope you will come there in person at some point.
Okay. Yeah, I hope too. So thank you so much for inviting me to give this webinar. Today, and so I will focus on the space weather at Mars, and actually I will organize my presentation in two major parts. First, I will introduce somehow space weather and the importance, the potential importance of space weather at Mars, describing some possible scenario of evolution of Mars atmosphere. So how space weather may have impacted the atmosphere of Mars along its history. And I will, in a second part, provide you some very recent observations by MAVEN, the NASA Scout mission, which is orbiting Mars since 2014. There have been a lot of recent studies published on specific space weather events at Mars, and it's very interesting to, I think, describe some of the main aspect of what happened at Mars during that event. So starting my talk, I'd like to go back to the origin of Mars, so something like 4.5 gigayears ago, and to replace somehow the different events occurring at Mars that we believe to know, on how they influence the evolution of the Martian atmosphere. So starting from the beginning, so at the beginning of Mars history, what we know that there has been at the very early time during the first 100 million years, there has been an active volcanism, an active giant impact at the surface, which shape globally the surface of Mars as it is observed today. So the two pictures you have in the on this slide are showing you the dichotomy of the rugosity of the surface as it has been observed. and as well as the altimetry, the topography of Mars, showing a clear, strong dichotomy between the northern hemisphere and the southern hemisphere, and which are basically associated with two different terrains of different age. The southern part being much older, more than 4 gigayears old, with respect to the northern part, which is more recent. I mean, has been shaped more recently. So very early at Mars, there was all this activity, volcanism, giant impacts, probably led to a very significant atmosphere. People are speaking of bars, between 1 or 3 bars of atmosphere at the beginning of Mars. Then the shape of the atmosphere, the surface as well, changed slowly. And what is important to remind is that thanks to many missions, there has been the indication that after this first very active period, there was still some activities at the surface of Mars, some outgassing periods, which lead to some very important features, topographic features at the surface of Mars. And these figures here is illustrating one of them, showing that there has been some fuel activities at Mars, even after 1 or 2 gigayears after the beginning of Mars history. So what we can say is that probably time to time there was a sporadic atmosphere, thicker atmosphere at the surface of Mars. Sporadic means lasting probably up to 100 million years, but not lasting all the history of Mars. So in other ways, the history of the atmosphere of Mars is probably very complex, with many episodes of declining atmosphere or outgassing periods. Altogether, there has been a big work done by people of Omega on board Mars Express. They analyzed the mineralogy signatures in the infrared provided by these instruments, and associating these mineralogic signatures with different terrains. And when you look to different terrains at the surface of Mars, what you can also reconstruct is the age of the terrain. So by associating some different age with some the presence or not of different type of minerals at the surface of Mars, they, I mean, people of Omega suggested a kind of history of the global history of the story of the atmosphere at Mars. So this is summarized on this view graph. So during the very first part, when the volcanisms was very active and giant impacts were also occurring much more often than today at the surface of Mars, this mineralogic signature suggests that there was some liquid water at the surface, liquid water which were non-acidic, leading to the formation of phyllosilicates. So there was, during, let's say, the few hundred initial million years, there was this liquid water which was somehow steady, or I mean, able to stay at the surface for a long time. I mean, leading to this major, for large range of phyllosilicate formation at the surface, as well as topographic signature, as I illustrated them before. What happened then is that around probably 4 gigayears ago, there has been some major change at the surface of Mars, because the liquid water which was then present at the surface of Mars was change of nature from a non-acidic features or characteristic to an acidic one, associated with the sulfate, to the formation of sulfates. So in other way, around 4 gigayears ago, there's been some major change at Mars. And after this second period, lasting also few hundred million years, there has been this very long period that we know today, which is similar to what we observe today at the surface of Mars, which is an atmosphere, a surface without significant amount of liquid water at the surface, a very dry atmosphere without with very few water at its surface, and lasting like this for the last 3.5 gigayears. So what's happened to Mars? This is one of the target of MAVEN, but before going to MAVEN, there was one thing which is very important potentially to explain this evolution. It was the presence of a dynamo, active magnetic dynamo inside Mars during the initial period of Mars. What we have learned from MGS, Mars Global Surveyor, on its, which was one of the first orbiter, after Phobos grant, after Phobos 2 mission, but the Mars Global Surveyor was put in orbit and had the opportunity to map much more systematically the magnetic field around Mars, and it revealed the presence of crystal fields. And what tells us this relatively strong crystal fields at Mars is that at a given time, long time ago, Mars has had an active dynamo. Also, the association of the crystal field with the terrain and the age of these terrains suggested that this dynamo collapsed, disappeared around 4.1 gigayears ago. So this is, and that's an explanation how people of MGS lead to this association, to this to replace this collapse of the magnetic field at Mars. They reconstructed the magnetization of the crust. And this figures here is showing you that, and showing that some big craters like this one were unmagnetized. And the fact is that when you have a big impact like this, you might lead to the unmagnetization of the crust. And so from the datation of this impact, which was more or less 4.1 gigayears ago, which happened 4.1 gigayears ago, you can infer when the dynamo was not anymore active enough to remagnetize the crust after this impact. So that leads to this datation of this collapse of the intrinsic magnetic field at Mars, which is very important because obviously when you replace these events on the view graph, on the slide, on the cartoon I showed you before, the end of the dynamo, which occur actually also in the same time with the last period of intense meteoritic bombardments that we know that occur in the inner solar system thanks to the moon observations. These two events occur more or less during this period when we think that the type of liquid water which was at the surface changed from non-acidic to acidic type. So something happened, maybe in relation with this end of the dynamo. Obviously, we don't have a direct proof of this correlation, but we have a correlation in time between these two events. So to add something regarding what could happen, so the fact that you change let's say you change from a planet with an intrinsic magnetic field to a planet without an intrinsic magnetic field, you will change the way the sun and the solar wind will interact with the atmosphere. So we don't have there is no, let's say, common agreement about the role of magnetic fields to protect or not an atmosphere, but what we can say very easily is that something changed in terms of interaction between the solar wind and the sun more generally, and with the atmosphere of Mars. And the second thing that has to be known is that we know also that the sun was not the same as at this time, 4 gigayears ago, than as it is right now. And one of the things which is very important to know is that the sun was probably less bright in the visible range, but probably much more bright in the UV range. And the UV range has a major role when it interacts with an atmosphere, because this is the range of the solar radiation, which is going to ionize the upper atmosphere. So by ionization of the upper atmosphere, you will also change this the way the solar wind will interact with your atmosphere. In particular, if your atmosphere is not anymore, let's say, embedded in a magnetic field. So that's one of the things which was very different early during Mars history. So the UV was much stronger. People are saying that probably 4 gigayears ago, from solar analogs that we observed elsewhere, that probably the EUV flux was somehow 30 times higher in intensity. In the same way, the solar wind the mass loss rate of the sun. The models of sun evolution are suggesting that the solar wind might have been between 100 and 1,000 times larger in flux than what it is today. So in other way, the picture we can derive from this evolution of the sun that 4 gigayears ago, when the Mars change of type of atmosphere, when Mars lost somehow its intrinsic magnetic field, we had solar conditions which were much, let's say, stronger in terms of the quantity of energy on materials which was impacting permanently the Mars atmosphere, were much larger than when they are today. So this is where we come to what we could learn from MAVEN. So MAVEN, for those who are not very familiar with MAVEN, MAVEN is a satellite, is a space mission, which is dedicated to the characterization of the environment of Mars. I mean, to the ion, neutral, and magnetic and electric field environment of Mars. In particular, to observe the way the solar wind is interacting with Mars atmosphere. So, and one of the goal of MAVEN is to reconstruct this, to provide some clues regarding the potential past evolution of Mars atmosphere. And one of the strategy for that is to consider that during specific solar events, so when you have some very strong flares which interact with an atmosphere, when you have CMEs, so this is here you have some illustration of some flares events here, and also from some CMEs which happened in September 2017. So when this type of solar events, solar energetic events, interact with Mars, you can imagine that you are going close to the typical condition that were happening at Mars 4 gigayears ago. Stronger UV flux and stronger solar wind flux encountering Mars atmosphere. So this is an analog. So this is why MAVEN was very, very focusing and put a lot of efforts to analyze what happened during this September 2010 event, because this is clearly one of the stronger solar events which encounter Mars during MAVEN operation so far. So there has been many works done around these events, and I will go through these events to illustrate you what could happen during this space weather events at Mars. So to go to this solar events, in the 10th September 2017, there has been X8.2 class flare events occurring at the surface of the Sun, in association with the CME. Obviously, the CME took much longer time to reach Mars, but what is illustrated on this figure is a simulation by NLIL, which is a NASA tool, which simulates the propagation of a coronal mass ejection in the solar system. And what you see here is that the prediction of NLIL on the 13th of September, this CME was reaching Mars and was really impacting directly Mars during this on that date. So that's what I'm going to show you in the following. Just a few words about MAVEN. I did not take time to give you some information. So I say that MAVEN. So first, MAVEN is PI is Bruce Jakowski from Colorado University, and MAVEN is fully equipped with many instruments which allow us to observe the electromagnetic ion neutral environment of Mars permanently. So this is a very, it's a relatively unusual. There has been no mission equipped with such a type of instruments. I mean, with the full range of instruments we need to characterize the plasma on neutral environment of Mars. So that was, it's really the first opportunity that we could observe directly space weather in full details at Mars. So going to this event, so the first things which I'm going to show you, so there is three major, let's say, inputs associated with these solar events. So this is illustrated on these figures here. So the top panel is showing you the EUV flux measured by an instrument on board MAVEN during this September month. So what you see here is on the 10th September here, there is this very large increase in intensity of the flux measured by MAVEN in the extreme EUV range, and we will see what has been observed in the atmosphere in association with this increased EUV flux. So as I said, three days later, there's been a significant increase in the solar wind flux. So this is translated in an increase of the solar electric field of convection, so which is a V cross B. So what we saw is an increase of the velocity as well as of the magnetic field intensity during these events. And in the same time, a very strong increase of the dynamic pressure. So the solar wind density was also increased significantly. But in association with the CME arrival at Mars, there has been a very significant increase of the SEP, so solar energetic particles precipitating into Mars at that same time. So I will go through these three parts of typical solar events that we can observe around the Earth of Mars, and go and illustrate you the different signature in the atmosphere which were induced by this different inputs from the solar events. So the very first is to start with the flare. So from the increase of the EUV flux. So there has been several papers published by MAVEN team. So this is one of the most interesting one, which show which measured the emission in the UV emitted by the atmosphere, by the main component of the atmosphere, the CO2 components, species, and measured by IUVS, which is a UV spectrometer on board MAVEN. And what is shown here is that, as you see in black lines, this is before and after the flare events. And in red lines here, this is during the flare events. So you see a very significant increase of the emission coming from the CO2 in association with the flare interaction with the atmosphere. In blue, you have the ratio between the average between the before and after flare events and the emission during the flare event. So an increase by a factor 2, which it translated in terms of density by a significant increase of the density. This has been interpreted by IUVS team by a flare signature which leads to the increase by 70 Kelvin of the temperature of the thermosphere of Mars. To replace that with respect to the typical temperature of Mars atmosphere, this corresponds to a 50% increase of the atmosphere. So it's a very significant increase of the atmosphere. So in other way, what they observed during the flare is that the inflation of the atmosphere gets much hotter than it is usually. And what is very interesting here is the fact that the after flare event, which was measurements performed few hours after the flare encounter with Mars, you can see that the atmosphere go back to its previous state. So in other way, the signature of the flare in Mars lasts only a few hours, 1 hour, which is also significantly shorter than on Earth. So this is basically due to the composition of Mars with respect to Earth. The fact that Mars has a very efficient cooling molecule like CO2. So molecules that can re-emit the heat they receive from the sun towards the space. So this is a cooling effect, which is making the signature lasting only a few hours. To continue on the effect which has been observed, there is another instrument which is onboard MAVEN, which is an NGIMS, which is a mass spectrometer, mass on ion spectrometer actually, and which can which measure locally the density of the different components of the atmosphere. And what they observe is illustrated on this figure. So same things. You have the X 8.2 flare events occurring at Mars, and in the same time, what you see. So this is the density measured at different altitudes, the density of the argon. So argon is a minor component of Mars atmosphere, but it's a very good tracer of the thermal state of the atmosphere. And what they conclude from this observation, from this very significant increase of the density at high altitudes of the argon, is that the argon density above. So before I was in the thermosphere, now I am above the exobase. So I am in the exosphere of Mars. What we see is a significant increase of the density also in the exosphere of Mars. And what they put some numbering here, what you see that you have a global increase of all species which are in the thermosphere. All the densities in the exosphere are increasing by factors between 2 and between 3 typically, on even up to 5. So this is a very significant change in the exosphere as well, induced by this flare. And last, the ionosphere. So obviously we could expect some important impact, because as I said at the beginning, EUV flux has led to the ionization of the atmosphere of Mars. And what is illustrated here is the variation of the electron density during before and after the flare event. So this is a dark line. The dark solid line is the average of what has been observed before and after the flare events. On the red line, like before, is what is observed during this flare event. So you see that there is very significant increase. The total electron density is significantly increased during this event. The temperature as well is increased. Here is decreased, but the profile is easier to explain using the bottom panels here, what you see here is the same plot than at the top, but plotted in terms of pressure level and not in altitude level. So it means that what they show is that basically to explain this change of the electron density, the easiest way is to simply come back to what I said earlier, that you have a global inflation of the atmosphere. So the altitudes, in somehow the atmosphere is getting inflated, and everything happens at higher altitude than in a before or after flare events. And this is very well illustrated by this plot, where you see this if you just rescale everything with pressure level, you see that what's happened in Mars is simply exactly what you would expect in a non-flare period, but simply everything changed in altitude. And this is the same for the temperature. The temperature is following exactly what is measured classically during before and after a flare. You have something changing at high altitudes, and this is explained by the change in composition. Basically, at high altitude, you change from a CO2, which is an efficient cooling molecule, to an atmosphere which is dominated by oxygen, which is a less efficient cooling species. So the temperature starts to increase when you have this relative ratio between CO2 and O, which change with altitudes. So in other way, we see this major change, and we see how much the atmosphere is impacted by these flare events. So continuing in my description of the different effects of this solar events at Mars, going to the effect of solar energetic particles. This is one of the most, let's say, impressive effects that has been observed. This is related to the auroral emissions. So IUVS observed a lot of auroral emission in the night side, obviously, because in the day side you are almost blind due to the air glow of the atmosphere. So in the night side, it's much easier to observe the auroral emission. And what is shown here on this figure is an observation, a map of the auroral emission, or of the emission, let's say, coming from the night side atmosphere, just one day before the CME on the SEP events. And just during these SEP events, what you see is a much brighter light coming from the night side, which is clearly an illustration that we see all these energetic particles precipitating into the atmosphere and leading to this interaction with the atmosphere, leading to these emissions that are observed by IUVS here. And what is also illustrated in this bottom panel here is a relation. So the dark point are the IUVS auroral intensity as observed the auroral intensity as observed by IUVS along the different time during this September events. And the color here are simply the SEP intensity measured by also another instrument by MAVEN during the same period. And there is a very clear correlation between the intensity of the auroral emission and the fact that you have a lot of SEP observed by MAVEN. So clearly showing you that during this type of events, you can expect a lot of change in the atmosphere, also induced by these solar energetic particles. And last, going to the last and most strong effect during a solar event, this is a CME. So coronal mass ejection are a form of dense energetic plasma, usually that in association with some magnetic clouds, which are going to interact with the environment of Mars. Here I summarize the CME characteristic by these two parameters we derived from the MAVEN measurement. So this is a solar wind dynamic pressure, which is illustrated. So what you see that there is on the 13th of September, when the CME reached Mars, there has been an increase by few order of magnitudes of the solar wind dynamic pressure. And in the same time, the solar wind electric field of convection was increasing also very significantly. So what's happened at Mars during that time? Very first things, we analyzed also the precipitation, the ion flux precipitation. So this is the precipitation at lower energy than what I showed before. So which we organize in two range of energy, a low range below 650 EV and a higher range above 650 EV. And what we saw during this event, so this is the same plot, but we zoomed on this on the 13th of September. So same thing, you have the increase of the solar wind dynamic pressure. And in association, we see a clear increase of the precipitation. So what we can say, which happened during this event, is that during this event, there was, because also of the flare, a lot of ions formed around Mars, and this ion has been accelerated and precipitating into Mars. The conclusion of this work was that the main let's say, parameters which induced this precipitation increase is the solar wind dynamic pressure. And so why are we taking care about this precipitation? Is that because when you throw EV ions like the one we are measuring here into an atmosphere, what you expect is some collisions at high altitude, which can lead to the ejection of atmospheric particles. And this is what is called sputtering. And this is also thought as a potential major mechanisms leading to the atmospheric erosion at Mars. So the conclusion of this work is simply that, okay, during high dynamic pressure period in the solar wind, you can expect some stronger sputtering occurring at Mars, and so probably also some stronger erosion of the atmosphere. in the same way, with the same idea to look to atmospheric erosion, there has been some observation by during the flare event. So coming back to the flare of the hydrogen in the exosphere, so also IUVS measurements, and what they observe is the increase of the density in the exosphere during this period, and looking also to the reconstructed temperature at the exobase of these hydrogen species, they concluded that probably during this special event of the flare encountering Mars, the hydrogen was lost with an intensity around 5 times larger than during more quiet period. The same for O escape. O is thicker, so it's less easy to be lost by Mars. But during these events, we think that the oxygen atomic escape increased by a factor 20%. So altogether, it means that during the flare, also the escape rate, the erosion of the atmosphere was increasing probably also significantly. And more dramatically, as I said, there is also some instruments which are able to measure the ion density and energy on MAVEN. And these instruments allow us to make some mapping of the ion escape rates during these particular events. So this is illustrated by these figures. Obviously, one of the difficulty to have one satellite around such an object during a CME encounter is that you have one point of measurement. So you have a very limited capability to map globally the escape rates at Mars. But what is suggested by this figure here is, so what is shown here is in solid line, this is the global ion escape rates as measured by MAVEN during very quiet period. And in red is specific observation done by MAVEN also, but during this CME encounter with Mars. And what you see that the escape rate can increase by a few hundred during very specific time at different specific location, as suggested by MAVEN. So the only way to, let's say, to get a feeling regarding the effect of the CME in terms of ion escape impact is to replace the MAVEN observation into a model, global model. So this is what has been done by different teams. So by Ma et al. And Romanelli et al. They simulate globally the interaction of the CME with Mars, and they lead to the conclusion that probably the CME like this, of this type, led to an increase of the ion escape by a factor 10. So one more time, to go back to my original plots, what we can infer from MAVEN during this specific September 2017 events is that the effects of, let's say, the solar conditions 4 years ago should have led to very significant impact on Mars atmosphere if Mars was not, one more time, having an intrinsic magnetic field at that time. So this is my conclusion that as I said at the beginning of this talk, we know from geological signatures as well as from mineralogical signatures that Mars atmosphere evolved quite significantly during its 4.5 gigayears of history. Probably lost more than 90% of its atmosphere. We don't know where did go this atmosphere. It might be that the atmosphere simply collapsed into the crust of Mars, but also that this atmosphere was lost to space. And this is the target of MAVEN to answer to these questions. And what MAVEN has performed so far is to suggest that yes, indeed, stronger solar conditions will lead to stronger atmospheric escape. And so probably it may be that indeed the early solar conditions could have explained a very significant loss of atmosphere at Mars. And so this is, to conclude this talk, this is simply a very, it's an illustration to explain how important space weather at Mars is, in the sense that we need to observe really many more solar events at Mars to really infer what could have been the history of Mars atmosphere along its history. And that will be my last word for this talk. Thank you so much for your attention.
All right, thanks a lot.
Thank you.
Yeah, that was a great talk.
Yeah. Can I ask a question, Dimitra?
Yeah, so let us, if you guys have any questions, please use the Q&A feature below. We have a question already. Chaitanya, I will unmute you so that you can directly ask the question. Just hold on. Yeah, go ahead.
Hello, I'm audible.
Yeah, please go ahead.
Yeah, I just want to ask about any comments of on magnetic paradigm functioning of Mars. That's how the magnetic field is being generated on the planet. Any comments on that?
I'm sorry. Can you? I didn't get very well your question. Can you repeat it?
I just want to know how the magnetic field is being generated on the planet, and how it is different from our Earth planet.
Okay, so this is a very delicate question. I hope I was careful enough not to state any strong argument regarding shielding by magnetic field, because I think this is a very debated question, and I think there is many arguments to argue that a magnetic field might not be a shield in the sense that protect your atmosphere from erosion. There is some suggestion that it is not. But honestly, for the time being, we don't have a very clear view about that. I mean, some people of Mars Express are arguing that if you compare the Earth, Mars, and Venus, you have very similar atmospheric erosion today, whereas on Earth, as we all know, there is a very efficient magnetic field, which is part of the interaction with the solar wind. So I think that the most careful statement that we can do regarding the potential role of magnetic field is to say that it clearly changes the way the atmosphere will interact with the solar wind. If it is less efficient or more efficient situation for erosion, for the time being, I think we don't have enough, let's say, modeling, theoretical analysis to really conclude about that. Do I answer to your question?
Yes, sir. Thank you so much.
You're welcome.
Yeah, so our next question is from Bob Johnson. Let me unmute him. Yeah, Bob, please go ahead.
I wanted to understand the relative importance of what the MAVEN team thinks the relative importance of the ion loss versus neutral loss. There was a paper by Bruce that suggested that maybe we've focused on neutrals too much and the ion loss may be more important.
Hello, Bob. Very nice to hear you first. And so that's true that let's say if we had to speak in terms of let's say in absolute numbers, which I don't really like because I think absolute numbers when we speak of let's say escape rate induced by a given mechanisms at Mars, absolute numbers are always potentially misleading, I believe. But anyway, what we can say is that if you take these absolute numbers as they are constrained by MAVEN, but you have also to be aware that obviously absolute numbers are associated with large uncertainties. So having said all that things, absolute numbers suggest that indeed photochemistry is probably one of the major mechanisms of escape. But I would say that I think if you want to replace these mechanisms and their effect on the Martian atmosphere, what is most important is really to look to their viability with solar conditions. That's the real key thing. So in other way, because as I said earlier, we know that the sun evolved quite significantly during this long period of time. We need basically to know better than how the ion escape, as an example, change with solar wind conditions. This is what has been observed during this CME. So this is very important to constrain as much as we can how each mechanism of atmospheric erosion did evolve along Mars history. So this is, as you can guess, this is why we hope that MAVEN will continue to operate and make measurements for a much longer time, because we need, to do that, we need a lot of statistics. We need a lot of, we need to observe these mechanisms during different solar conditions. And so far, unfortunately for MAVEN, we arrive at solar almost at the end of at the beginning of solar minimum, and most of the observation of MAVEN so far have been performed during solar minimum. So not that much solar wind variability, solar variability.
Okay, thanks.
Hi, can I ask, can you hear me?
Yes, yes.
So I get the impression that the change in the atmosphere of Mars is more the result of catastrophic events rather than normal processes. Is that a correct impression?
Are more due to what? I didn't get
catastrophic.
Oh, what would you call catastrophic?
Well, huge local escape of ions, for instance, are result of strong solar flares hitting the Mars atmosphere because there is no magnetic field and things of that sort.
Yes, but actually, I think we can say something slightly different because, as an example, when you look to the flare events, what is also, I think, what one of the very interesting observation by Maven is that the fact that the atmosphere gets back to its previous state within 1 hour, which is very quick.
I see.
So there is a kind of the atmosphere is able to let's say to sustain this stronger solar conditions and react quite quickly. I mean, because of CO2 cooling. So it's really related to the specific composition of Mars upper atmosphere.
Okay.
Yeah.
Thank you.
Yeah, Bob, do you have another question? I see your hand raised.
Yes, just the new mission from the Emiratis. What will that add to Maven's understanding?
I believe that they have a very good UV spectrometer. On the part of the observation I show today were from this instrument. So this is a very efficient tool to, let's say, to figure out what the state of the upper atmosphere, the state of the exosphere, and to provide some information also about the atmospheric escape. And what makes this mission very interesting as well is the fact that they also have some, let's say, different instruments to characterize the upper atmosphere state during this in the same time. So it means that the clue, basically, when you want to understand Mars on its way to interact with the sun, is to make this relation between the lower atmosphere, the upper atmosphere, up to the exosphere. So to follow these different links between these different parts of the atmosphere. So clearly, this is a mission which will provide us some clue regarding this relation. And so on the last thing that they will arrive probably during a slightly more active sun period, which is also very, very good to follow this variability that I mentioned before.
Okay. Thank you.
Yeah.
Thanks. So one question I had was that, you have different channels of escape and you have different models taking these different escape mechanisms into account, but you have one observation. And so how do you determine the relative importance of which escape mechanism is more relevant? Is it based purely on modeling, or can you say something about it purely based on observations?
I mean, this is, I would say, unfortunately, this is highly dependent on modeling because it's, as I said, it's really uneasy to reconstruct with one satellite the different, I mean, the escape or the erosion effect on various solar conditions, because as you can imagine, when you are measuring the ion escape, you don't know in the same time the solar wind conditions. So you have to reconstruct all these parameters with some assumptions. And moreover, you have also only one point of measurement. So we know that, as an example, the ion escape is really structured in the magnetosphere in the induced magnetosphere of Mars. So it means that you have some channels of escape in different part of this magnetosphere, and so to have to be able to really reconstruct globally the escape, you need to replace one single point observation into a global 3D map, and only modeling can do that for the time being. And so, yeah, clearly we need models for that. And then the key things that we need to know is how the environment of Mars, the upper atmosphere, the exosphere of Mars change with solar conditions. So this is very efficient information to tune somehow the models. I mean, to see, because what you ask to the model is to be able to reproduce the variability of Mars environments for various solar conditions. So observations are giving you some clues about the way this environment change with solar conditions, and models as to, let's say, as the very first things, have to reproduce this variability. This is a very important proof of concept for the model. And when your model follow more or less this evolution as observed by MAVEN or other spacecraft, then you can think, I think, to have a good tool to extrapolate to past conditions what could have been the different channels of escape.
Oh, thanks.
Yeah, please.
I have a quick question. Can you hear me?
Yeah.
Yeah, okay. So this was something you touched on early on in the presentation, and if I understand correctly, that there is a possibility that such large-scale impacts at Mars early on could have unmagnetized or diminished the magnetic field of Mars. So I was curious if there's an analog to processes at Earth, which obviously does still have a magnetic field, and then processes at Venus, which to the best of my knowledge does not have one. So I was curious if there's any kind of similarities or differences in the original formation and the initial hundreds of millions of years of those other terrestrial planets' evolution in the solar system. And it seems like Earth is in another Goldilocks zone with a magnetic field surrounded by two terrestrial planets that don't have one.
Yeah, this is a very vast question because it's a very complex issue. I will start to say that what makes Mars for me very difficult to be compared to with the Earth on Venus is simply its gravity fields. You really, when you look to Mars atmosphere or even upper atmosphere, exosphere, there is major differences in the composition, in the structure, and the density of this region of Mars with respect to Venus on the Earth, simply because of the gravity. So on one thing that make me doubtful regarding any make me doubtful about that we can easily compare Venus or Mars to non-magnetized objects is the fact that you have to compare the size of the object. When you start to speak of absolute numbers, I think you really have to look to the size of the object. And by size of the object, I mean the obstacle to the solar wind object or to the sun. So when you have an object like Venus, clearly you have an object which is almost 10 times larger than Mars in terms of region of interaction with the sun on the solar wind. So you have to scale already everything with respect to this size of the object. And when you are thinking to the Earth, which is magnetized first, but the magnetosphere of Mars is huge with respect to the size of Mars obstacle to the solar wind. So I think really you have to take that into account when you do even direct comparison between these subjects. So that makes the things very complicated because in other ways they are not the same objects. The obstacle they are placing against the solar wind is completely different. A magnetic field on one side and an atmosphere on the other side. So it makes this, I think, the comparison very complicated, and I will, let's say, I will be always very careful to make any comparison. But I think definitely we need to use this planetology comparatives capability we have to compare them, but with a lot of care.
Fascinating. Thank you.
Yeah.
Yeah, we have another question from Bob.
Sorry. Yeah, but a guy named Walter Scheid, who wrote a paper, is part of the MAVEN mission, suggested wave activity may play a role. Is there any evidence for that? Mars.
Can you repeat that, please?
Wave activity. Is there any evidence that
Oh.
the very active wave activity on Mars plays a role in the escape? Or is that not?
I honestly, I don't know. I know that wave activity are very, I mean, that's one of the, let's say, most surprising observation by MAVEN. I think that you see waves activity very high in altitude, very changing the composition, having signature in the thermal structure of the atmosphere. So clearly, wave activities are very important. This is mechanisms for the atmosphere to, let's say, to react to the external forcing. So clearly, that has to be considered. My concern is that I think we need a lot of studies of the type you have done, Bob, to dig into this, the effect of these waves on the final structure of the atmosphere, on its evolution. So clearly, MAVEN opened this let's say, discover somehow this aspect of Mars atmosphere. But I think we are at the beginning of that. So we need more theoretical modeling, as you did. We need more observation, as MAVEN did, and I think that's clearly one of the key things to look to. Yeah.
Thank you.
All right, thanks a lot. If we do not have any other questions, then let us thank the speaker once again. And yeah, thanks a lot for being here. And
thank you very much.
And next week, we are going to have the Mars Symposium with many people discussing all the upcoming Mars missions, results from earlier missions. And Franco, you're more than welcome to attend, and your students, colleague. Yeah. So thanks a lot, everybody.
Thank you.
Nice talk.
Thanks a lot. I'm trying to leave the meeting.